This talk can be pretty casual. I think if you want to shout me down and interrupt me, by all means, do that. Otherwise, I'll just sort of move through it. What I want to talk about is shape learning, and specifically, we'll get to sort of parameterization invariant representations. But what do I mean by shape learning? I'll draw a commutative diagram. We have a space of parameterized objects, and we do the usual thing. We project this onto shape space, right? Which is just the parameterized objects modulo reparameterizations. Oh, my script D is not so good. Okay. And we have some function down here that we want to learn. Some function that depends on the shape of an object. But objects are never given to us in the real world as shape classes. So we really have some function here that we want to learn. F, right? Some output space. Let's not get too worried about that. That is invariant to the action of reparameterization so that it sort of factors through this projection, right? The general setup. Okay, so a question that we might want to ask is if we are trying to learn such a function, how can we ensure that our approximation of our function is maintaining this invariance to the reparameterization group? And how can we represent data with a fixed dimension? If we start to think about things like triangular meshes, they have differing number of vertices, differing connectivity, and so they sort of live in a different dimension as far as the computer's concerned. So how can we represent these with a fixed dimension? And the trick that we're going to use is these parameterization invariant latent space representations. So I'll go back to my diagram here. Let's cheat, break the problem into two problems. Let's just put some other space. I use a script L here. Design some function E so that E is invariant to the action of reparameterizations. So E factors to the projection. Get those dotted lines. And now let's just learn a function G so that E composed with G is approximating F, right? So obviously there are some problems here, like E needs to be as injective as F. There are issues, but if you have a well-constructed map E to some finite dimensional space, you can see how we would want to do this, or we could do this. Okay, why would we want to do this? Well, E, we said, is constructed to be parameterization invariant, which is nice. So why decompose it this way? Just go ahead and get all the pictures up here. Why decompose it this way? E is going to be invariant to the action of reparameterizations by design. Sorry, I'll stop standing in front of it. And so then G composed with E is going to be invariant. So now our approximation of F will be invariant. And also, E can be designed to not depend on the dimensionality of the discretization of data from our space of parameterized objects. Okay, I've been doing this all like vague parameterized objects, not saying exactly what I mean, because this is not necessarily new. In fact, a very well-known framework, PointNet, is exactly within this regime. So how does PointNet operate? Well, it considers point clouds, which are sort of ordered lists of points in 3D, and it learns a latent space representation that is invariant to the reparameterizations of point clouds, which is just the symmetric group on an element. So it sort of learns this invariance by doing the following. It learns a map from R3 to R1024. It takes your point cloud in 3 dimensions, pushes it to a point cloud in 1024 dimensions, and then it takes an element-wise average, and since this addition is invariant to the symmetric group, this representation is invariant to the symmetric group, and so now you have invariance exactly to your sort of notion of reparameterizations in the realm of point clouds. Other symmetric functions can be chosen, and in fact, I think what they actually suggest in PointNet is to use like element-wise max pooling. PointNet spawned a bunch of other methods to do this same generic task of mapping your point cloud into a higher dimensional space and then hitting it with a symmetric function. And the main difference between these is exactly the architecture of this map M that they learned to push the point cloud into a higher dimensional space. So you have things like DGCNN, which uses some nearest neighbors computations, or TCPNet, which also uses some other local information to map points into a higher dimension. And this now gives you exactly something that is invariant to the appropriate reparameterization group for point clouds. Okay? But I don't really want to work with point clouds, as you might have expected. I really want to deal with surfaces. So in the context of surface data, our space of parameterized objects will now be the emergence of some regularity of a 2-manifold into R3, and the group of reparameterizations will now be the diffeomorphisms of our manifold. So things have gotten ugly and infinite dimensional, but we'll try to sort of get through that. So you could think, well, I'll just apply PointNet to a sampling of points from M. Just take some sample of points at M, map them into R3 via Q, and then operate on this point cloud. This might be like the straightforward thing to want to do. A couple problems here. You sort of ignore all of this continuous data. So somehow the signal that exists on your shape is lost, some of it, maybe not all of it. And this, of course, depends on the way you sampled your points on M. But also, this architecture is really only invariant to reordering of your points and not to really full diffeomorphisms. Not really invariant to the, I'm going to say, appropriate reparameterization group, sort of in air quotes there. So despite this, state-of-the-art frameworks do exist that basically do exactly this process, where they apply PointNet to a sampling of points from M mapped into R3 via immersion, right? So the nice thing is we also have ways to get parameterization invariant representations of surfaces. In particular, a varifold, right? So the varifold, right, is just a measure on R3 cross S2, which is the push forward of the volume form of your surface via your surface itself and the Gauss map of the surface. If you're particularly familiar with varifolds, you know I'm sort of burying this Grassmannian consideration. I'll deal with it when we put a metric on the space. But before we put a metric on the space, there's a question. Here we have a nice parameterization invariant representation of a surface, because we can take any reparameterization gamma, and the varifold associated with Q acted on by gamma is exactly the varifold associated with Q. But it's not yet in a finite dimension, certainly not a fixed finite dimension. So to represent a varifold in a fixed finite dimension, we need to solve some quantization problem. And we're not going to do that. There are sort of some approaches going on, some new approaches coming out where you do quantization in the space of varifolds. But I am going to not consider this approach. And instead, I'm going to present a cute little computational hack. I think it's cute. So for my cute little computational hack, what we need is a distance function on the space of varifolds, and we're not going to take anything special. We're just going to take sort of the normal RKHS norm that is put on the space of varifolds, where for two surfaces P and Q, the scalar product between the varifold associated with Q and P is written exactly as this double integral. You can see we square this radial kernel, so we don't. This problem of this not really being the Grassmannian is sort of dealt with, pushed under the rug. Okay? So, we're now going to leverage this distance function to get a representative of shapes. How? We're going to fix a template shape, so some parameterized surface T that's discretized by a triangular mesh with M vertices, and we're going to compute the gradient of the varifold norm squared between our input data, the varifold associated with our input data Q, and the varifold associated with our template with respect to the vertices of the template. So, and then, yeah, there's sort of this nice little fact that this can really be written as the gradient of the scalar product plus some constant vector field that we will mostly ignore. So this is a vector field on our template surface, which is going to be discretized on the vertices, so it will always be m times 3 dimensional, independent of the dimensionality of our mesh representation of Q. Intuitively, it gives us sort of a first order approximation of how to deform the template into the target surface Q. So there is shape information encoded with this representation. And due to the properties of varifolds, it's parameterization blind and robust to imaging noise. So we have some examples here. We've got the template surface in light blue. We have 3 surfaces seen as inputs in dark blue. This is a really highly sampled human body. This is a downsampling of the same human body. And this is a downsampling of the same human body, but there's some artificial imaging noise. So there are holes artificially added. They don't show up great on the screen, do they? There's one down here on the thigh. There's some on the forehead. But the upshot is the varifold gradient represented by this vector field on the template object is the same for all 3 of these. And I think in the eyeball norm, we would agree that all 3 of these are the same shape. So we are sort of encoding the shape information, and we are blind to parameterization and robust to imaging noise. Okay. So are there any questions at this point? Sort of pause. And yeah. So, great. We have a finite dimensional representation of surfaces that is parameterization invariant. This was the goal. The question is, how useful is it? The constant vector field, or any constant vector, in fact, would be a parameterization invariant representation. It just wouldn't be very representative. So how much can we learn from these varigrad vectors? So the first example we'll use to, yeah.
If the shapes are not aligned, there's like, if I rotate a shape, it's going to change its representation, right?
Yes. Yeah. This is.
If you're far away, it might be a bit odd, right?
Yeah. This is sort of assuming a priori that you have alignment and rotation and translation. I mean, centroid alignment for translation. Rotation's a little more difficult, but in all the examples I'll talk about today, everything's just been aligned via translation and the data comes in already aligned with rotation. Yeah, I mean, this is actually like a problem we are still having with the framework, is that, yeah, there is no way to avoid needing to do this pre-alignment. This is something would be nice, and if anyone has any ideas about it, I'm certainly open to discussion. But yes, good point. Okay, so consider this I sub f as a subspace of our space of all parameterized objects, which are, let's say, surfaces of a specific modality. In this case, they will be human body scans that can be represented by a mesh with a fixed mesh structure F. So this means the triangles are the same and the vertices are ordered in the same way. This is what I mean by fixed mesh structure. And our goal is to learn a function from sort of all of the parameterized objects, at least some subset of the parameterized objects, into this sort of more constrained space. so that we're getting effectively the same shape back. So it's the problem of reconstructing the shape with a fixed mesh structure, which gives you then point-to-point correspondences between the output of your model. So we're going to try to learn such a function on the DFAUST data set. I don't know how many people are familiar with it, but it's approximately 40,000 scans of human bodies. And it also comes with pre-registered data. So there's a fixed mesh structure they have with their data that you can use with registered versions of the meshes. Mesh is represented in the exact way we sort of want to learn. So we can train the model now, which I have an architecture here, take a surface, compute the varifold gradient, feed it into some decoder. I'm suppressing a little bit of this in the interest of time to get a output that has the same mesh structure as our template, in fact. This doesn't necessarily have to be true, but it has a fixed mesh structure. All of the meshes coming out of our model have a fixed mesh structure. And we want to do it, well, in the unparameterized case, we would do this to minimize something like the varifold norm between them. But we're going to train just with the registered data. Because we're already robust to reparameterization, we can just train exactly with the registered data, and it will still work on unregistered data exactly the same. And we can just minimize the mean square error of the vertices, of the meshes. So really we don't have to put a lot of effort into the loss function when we use the parameterized data. So we take 80% of the data to train with, approximately, and we just minimize mean square error between our inputs and our outputs. We get the following results on both the unseen registered data and the unseen unregistered data, so the raw scans. So I won't dwell too much on the numerical thing here, but we perform, I would argue, maybe slightly worse than 3D coded in the case of parameterized data, which is exactly the modality of data that was given to us for training. Right? But when we go to the unregistered data, we basically see no drop off in our own performance, but 3D coded starts to lose some performance. Also, because 3D coded has this point net map M that it also needs to learn the parameters of, it does require a little bit more time in training. Our model has actually quite lower numbers of parameters than the DGC or 3D coded model. And 3D coded does surface reconstruction with an optimization step. So they optimize in their decoder the latent variable. Won't get into that too much, but we can perform these reconstructions significantly faster and with similar accuracy on raw scans. So here's some qualitative results. I don't think they're particularly remarkable other than to say we are in fact recovering the shape. For all of this input data, we are recovering the correct shape. As is 3D coded, but it doesn't have to be a competition. Now let's make it a competition. No, I'm kidding. But we want to now test the generalizability of both of our models and the robustness to reparameterization. I mean, this is the pitch of this variegrad representation, is that it is parameterization invariant. So we took 100 of the unseen surfaces, and then we resample each surface 100 times. So we sampled a bunch of points from the surface, remeshed, and we got 100 resamplings of a surface that sort of looks like this. They have some pretty significant noise. Sometimes the remeshing fails somewhat spectacularly. But when we feed all 100 of these resamplings of a mesh into our model, we create these 100 outputs. As you can see, we're really stable to this resampling process. 3D coded starts to have some issues. You see that there's some variance in the output. There's some numerical results too. So when we take the whole 10,000 surfaces and we just test the error in the chamfer distance, we keep the same error we saw in the unparameterized case. Chamfer, or 3D coded starts to, again, lose some performance on these really extreme resamplings of the surfaces. And then within each of these 100 classes of 100 resamplings of the same surface, we measure the variance and then take the mean, and we have orders of magnitude lower variance when compared to 3D coded. So this should give us some indication that just throwing these point net-based models at surfaces is not the thing to do if we really want to have parameterization invariance of our outputs. That's the upshot of this experiment. Any questions at this point?
It's not aligned anymore at the output. Perhaps you see the head is not aligned with the head.
Yeah, there's some. So 3D coded predicts an initialization of then a minimization of the chamfer error. Getting a little more into the details of 3D coded. And so if your initialization is bad, they have some really nice examples in their paper. If your initialization is bad, you really won't get close to the surface, and you'll have something that's sort of tragically wrong, like this sort of misalignment. And that's exactly what happens. Because they're not consistently getting the same output, some of the initializations get them far enough away from the correct answer that then when you run this chamfer minimization, you get this misalignment. Yeah.
3D coded is learning the template now, as it goes. I forgot.
No, I think they have a fixed template in the model that we use.
And you are also not touching the template?
Yes, we're also not touching the template. Yeah, I sort of vary some of the model in just wanting to argue that varifold gradients are useful and not really get into the details of the model, but we could discuss that more later if you're interested. Cool. Okay. So now I want to spend a little bit of time talking about, I forgot to talk about all the colleagues that I had listed on the first slide. So with the group of colleagues I had listed on my first slide from Johns Hopkins, we're currently working with some data that I find really interesting because it's some kind of neat real world data, which is 3D surfaces representing left atrial appendages of 543 patients, some of which have had ischemic stroke. And it's sort of well understood within the sort of medical community or some sub-community that this morphological changes in this part of your heart are heavily correlated with increased stroke risk. So there's this nice study, which one is it? Yeah, the Biaz et al., which what they do in this is they manually classify each of their left atrial appendages into one of 4 morphological classes, and then they measure the relative stroke rates of those morphological classes, and they see one of the 4 really has a much higher stroke rate, and one of the 4 has a much lower stroke rate. But they have to do this manually, so someone has to go in and say, this is class A, this is class B. They have funny names, but I'm forgetting them at the moment. Like a windsock and a chicken wing. Yeah, I forget all the details, but the names of them are in this paper here. So I have some examples here of these left atrial appendages and the varifold gradients on a template that we just sort of selected from the data set. And we want to do a couple of experiments. We would like to automatically cluster, based on the varifold gradients, this data into 4 classes and see if we also see different stroke rates among the automatically clustered data. And also, we would like to potentially train a support vector machine classifier on the varifold gradients associated with these surfaces to be able to see how at risk, right, someone is of ischemic stroke associated with a morphological change in their left atrial appendage. So we train this model, this very simple SVM, on 143 of the patients and then tested on the remaining 400. So pretty aggressive training testing split. So first, the clustering. I will say that this is like absolutely not the metric you should use on the varigrads, and it was just sort of the first thing to do. We took standard L2 distance between the varigrad representations of the data, and then we used some spectral clustering method, set the number of clusters to 4. These are the sort of 4 centers you see of these 4 clusters, and then we compute the relative stroke rates. And what we see is numbers very consistent with what you saw in the previous paper where they did this manually. One group here with this sort of nice smooth left atrial appendage has a stroke rate of 3%. Groups 2 and 4 have a stroke rate around 7%. Group 3 here has a stroke rate of significantly higher. Right? So this is kind of nice that this fits with the existing understanding of this problem from people who are not using automatic clustering but doing it manually. The SVM classifier, I don't think these are particularly good results, but when I showed them to the people I'm collaborating on this project with, they were quite impressed. The SVM classifier gets an accuracy of something like 83.5%, so it's not incredible. Of the mistakes, or of the 400 testing cases, 10.25% are false positives and 6.25% are false negatives. And the really cool thing that we can do when we've used the model this simple is that we can visualize the discriminant direction of the support vector machine as a varigrad, which tells you, in some sense, the direction of the deformation that most leads to ischemic stroke. So I have these results here, which are fun to look at and interpret, of the same 2 LAA meshes, the associated varifolds, and this is the direction which points towards positive classification of ischemic stroke. And what you can see if you look and stare at it for long enough is that the inner product between these vectors and these vectors summed up seems to be higher than with this varigrad and this varigrad, and that fits consistently with what is actually known about this data, which is that this is an unhealthy LAA and this is a healthy individual. Right, so we're able to really visualize this deformation, and from looking at this data, maybe it takes a little bit of time, you can also see that this is correctly identifying the sick patient and the healthy patient. Okay, so there's the results on that. How much time do I have left? Oh, I'm doing okay. So we propose using the gradient of the varifold distance as a parameterization invariant feature to represent surface data. We sort of demonstrated through a couple of numerical results that it is successful at shape learning tasks. Yeah, we should talk about some examples of using more classical learning rather than deep learning methods and how this leads to improved interpretability. And there are a few open questions, I think, that still exist that we are studying as future work about the varifold gradient, namely the sensitivity of the varifold gradient with respect to your choice of template. So in practice, we've been mostly just taking a random piece, like element of the data set to choose as our template and not doing anything particularly well-informed, but understanding the sensitivity of the varifold gradient to the choice of template is something that I think would maybe help out this sort of framework. And also characterizing the kernel of the varifold gradient operator, because there's no real reason that 2 distinct shapes couldn't potentially get mapped to the same varigrad representation, and this would be a problem if those distinct shapes take different functions in whatever function, or different values in the function that we're trying to learn. So this could be potentially harmful. So understanding the kernel of this varigrad operator is something that we'd like to do. originally I had these experiments organized differently, so this made more sense on the last slide. But I just wanted to highlight the human body reconstruction experiment that we did. We were able to really use it on new data, which was just a 3D scan I took of someone with my phone, segmented it out a 3D mesh, and immediately had a representation which had fixed point-to-point correspondence to a lot of your typical human body shape models. So this was kind of a cool result. Okay, I think I end a little bit early and maybe take extra questions. So thank you again to the organizers for inviting me to speak and all of you for paying attention on this Monday afternoon.